Heard that. Mm-hmm. Okay, cool. That's 10 more points for you, Alika. I hope you're tallying your points up. All right, so this problem is located on what page, Ms. Ryan? You didn't say that part. Oh, she said, actually saying she grabbed the book. How cool. All right, I hope you two are catching up. We're about to do what we do. Ashley and Carson. All right, so look, flip this page. Go to page 758. The very first equation you're going to need is the equation for equivalent resistance, just like he was talked about on our do now here, right? So if we look at this, that equation is, again, the equation for equivalent resistance. Okay? Oh, she's telling me what it is. Yeah, all right. So let's break that down. Let's unpack that, right? So equivalent resistance is known mathematically as R subscript. You know how to use subscript from Google. Just go up there and hit subscript, right? You bring it down some. You're going to break my headsets. I see you over there, my man. All right, that's cool. Don't respect the equipment. All right, for a series circuit, this is series. We're going to see next week how that looks for parallel, right? But that's R1 for resistor 1. Like y'all have y'all resistors in the circuit, right? There's a little brown little resistor part components that slow down the current. Plus R2 plus R3. You know what those are? That's the other resistors. And then plus, if you look at the box, dot, dot, dot means if you had an R4, R5, R6. We only have 3 resistors in series. And that's the name of the problem, actually. So if you look down on page 758, this problem starts on 758 and it ends on 759. And that's why I kept on rushing y'all with the simulation. I wasn't being evil, but if you look, it's 2 pages long of work. So we gotta get busy, right? And you got a U-do, and yeah, you just change numbers, but there's a lot of work still, right? You gotta do the work all over. Now, lucky for you, you're typing it, because all you gotta do is copy everything we do here and change the numbers over there, grab your calculator again, and you're done, right? Okay, so let's get that done so you can get your exit slip and your U-do done on your own, right?
Hey, Tyler, what y'all looking at?
What page? 7, right, yes, sir. Well, we just looked at the green box, Carson, with the equation here, and I was explaining how you're going to turn all these resistors, kind of like, I'm kind of giving my age away, like Voltron. Anybody ever see the cartoon Voltron? It's like an old school cartoon where all the lions come together and they form a body and the head comes down. And, okay, well, what about Power Rangers? I know it's around your age, right? Yeah, okay, I know. Yeah, Mighty Morphin, all right? So, yeah, whatever. But they came together, right? So, the resistors, tell my age, I didn't watch that. Voltron was cool. I had the tall figure. But anyway, like right here. Anyway, we have our tool, and our goal here is to find out, one, because there's 2 parts to this, right? When she read it, the resistance of R3. R3 is inside of here, so we're going to do some algebra to get it out. And then the other part, that's part A. Part B is the potential difference. If you don't remember what potential difference is, that was what? That's our battery. We just played with that in the simulation. That's also known as your electromotive force, depending upon the circuit you're working on, or just basically your voltage. All right, that's what they mean by potential difference. To get potential difference, you're going to need another equation, which is similar to the equation you just used called Ohm's Law. So here's what I mean. So you have this, but you also need Ohm's Law again. And Ohm's Law is composed of what? You saw yesterday. V equals I times R, right? Another way to write that, though, which you'll see is helpful here, is what? Well, you could write, this is epsilon, which is electromotive force, like we saw before, right? This is also synonymous with voltage, just a different way to apply it, is equal to your current, which never changes in a series circuit, multiplied by your equivalent resistance. These are almost identical. They're just 2 different ways to write it. Huh? What's the one? Yeah, well, you remember epsilon? Yes. That's that lowercase Greek e. Yeah, we did that all last week, right? So write all this down because you're going to need it for Friday's quiz. And yes, you have a quiz coming up. This is a big problem in quiz too. All right, so get all your notes you can on this. Now we're about to delve into what we know and what we don't know about our problem. So I think it's like 3 components or 4 or 5 components to this. It's a lot of work, so just try to keep up. If you think you know the answer, yell it out. And if you're right, I'll give you 5 points, right? So what do we have here? Let's write known. What do we know? We're setting up our ingredients. He said volts. All right, hold on. Now, what is the letter for that, sir? No.
V.
Hold on. The what? The E. V worked yesterday. Oh, he took his teeth. 5 points, though. But she's right. That's why I said use this version because we're dealing with electromotive force. Anytime you hear potential difference, you should automatically, okay, that's probably electromotive force, right? If you say battery by itself, you could use V equals IR because they use volts. Okay, so epsilon, she's saying is 26 volts. Very good. Did you add 5 to that? Carson, I gave it to you too because you said V, but I knew you was trying to get the right word. All right, what else are we giving here? You said it though, Carson. You was wrong. What did we? Yeah, which is?
0.
No, what letter? Because you said it earlier. Now you got it right. You said I earlier, and you was looking for this. So go ahead, sir. He said I. I was like, no, not yet, bro. What's the number you got though?
0.0444.
Okay. It's 3 fours or just 3 fours? Oh, what's that? Actually, what you beating up your desk? Oh, she dropped the book. What you doing, girl? Okay, that's 5 points for that gentleman. Now, moving on. What else do we have here?
I got 40 points.
I don't know. You're supposed to be see, I knew you was going to do that. So keep it on your points, man. R1. She said that's strong. And that's equal to what there? 250 ohms. Thank you, man. You got 5 points for identifying that one. And make sure you use omega, which is our Greek symbol for ohms. Don't write ohms everywhere. Find that symbol, copy and paste it wherever you need it for resistance. 5 more for the leak, I said, but do you know what else we have here? Just look at the problem. We got some more to go. Known and unknowns. What else do we? R2, and what is R2 going to be? 188.78 ohms. So 188.78 omega or ohmic. All right. How about what we don't know? What is this question asking us? You got a part A version and a part B. R3. Okay, so R3 is something question mark ohms. Gotcha. We're going to figure out what that is. I can't write omega today for some reason. All right, what about part B though? What we got? We don't know what part B is? Well, part B is basically your voltage values. So you're going to need to find V1. And if you want to follow what I'm doing, now I'm on page 2 or 759, where the problem continues, right? So V1 in volts, which I'm going to do, and then you're going to do V2. And V is going to come from Ohm's Law when you get to that point. So don't get scared. You're going to use this from here on out. Volts. And then V3, some number in volts. All right. Told you a lot, right? How we doing on time? 12:45. We got 15 minutes class left. Let's burn this problem. We have everything we need. Let's get to work. All right. So first things first. You need to get REQ so you can find R3. We're going to do some reverse engineering here. So you're going to use this equation right now and solve for REQ. Because why? We have our electromotive force, right? We have our current, so we can actually find REQ and then go back and find R3. Let's do this. So step 1. You're going to solve for REQ, and that is via, or using, I should say, your Ohm's Law. Okay? So we know that, we're going to rewrite it. So that's, what did I say was? Electromotive force is equal to current multiplied by your equivalent resistance, right? Right? And then I'm going to rewrite it again because we're going to work on it. So here's an iteration. electromotive force is equal to current multiplied by your equivalent resistance. And then what do I do here to get REQ by itself? Well, I thought y'all would know. I mean, it's your favorite word. Thank you, sir. I know somebody knows this one. He always says divide anyway. The reason we divide, he's right, because this is multiplication right here. So we do the opposite. This is like a strong reminder of algebra. So we're going to divide by I because we want REQ by itself. Current crosses out. And normally I would slow down and let y'all figure it out, but we don't have a lot of time, so I'm just burning through the math with you. And then you have to try it out on your own, and you do. All right, so moving on, rewrite the equation. We now have REQ is equal to your electromotive force divided by your current. Plug and play. We know what they are. Let's plug it into this equation. So REQ is equivalent to what? Well, we know the top value for voltage is 26.9 volts, right? Bottom value, denominator is current of 0.0444 amps. Okay? I'm going to go ahead and calculate this for you, or if somebody knows, it's 10 points. If you don't worry about it, because you don't have a lot of time. So when we plug this into our calculator, we get, make sure if you're using this, you hit the fraction button. It's underneath the delete button right by the book. So that's 26.9. Dang, we spent 11 minutes on this problem. It's going to get longer. 0.0444. I get a yield of 605.86. And that's going to be in ohms. So 605.86 omega. All right, we'll box that for a second because we're going to use it over here. Next step is solve for what? What we tried to find originally, which was R3, right? So to do that, we're going to use this equivalent resistance equation up here. So that is equivalent to saying REQ, right, is equivalent to R1 plus R2 plus R3. Continue on. We got to get R3 by itself now using algebra again. So this is a super algebra problem, basically. So let's do that. I'm going to rewrite it. I'm going to have REQ, let's come on down, is equal to R1 plus R2 plus R3, right? And then to get rid of everything around R3, I just do the opposite. So since both of those are positive, let's include some negative resistor values. So to do that, I just say, hey, I want to get rid of R1. So that's minus R1. That'll annihilate these two. And then minus R2. That'll annihilate the R2s. But what you do to one side, you got to do to the other. So it's going to be minus R1 minus R2. You put a little plus sign there so it's all mathematically correct. Now these things cross out. So our R1s and R2s are gone. These are gone. We have a whole new equation now where it's R3 is equal to, just rewrite the rest over here, just writing it right correctly mathematically. So it's minus R1 minus R2 plus REQ, right? So let's plug in the values, because we got REQ now. We're going to take that and use it here. So what does that look like? Well, that becomes simply R3 is equal to, so I'm going to get a little long over here. So minus, use parentheses, what was our R1? That was 250 omega. What else? Minus R2, which was 188.78 omega, plus REQ, which we figured out was 605.86. And that's omega. Okay? So now we're going to calculate this. I'm going to do one part of Ohm's Law with you. It's not 12:51. So you got till tomorrow to finish everything, right? Because y'all just redoing and doing your exit slip, and I want to finish this up. So look, pretty much the next step is, let's calculate it. Because we run out of time. I think it's going to take 15 minutes to do this problem. But I knew it was long last night when I saw it. So minus 250, right? And minus 188.78. Plus somebody's calling me and I don't know why. People like to chat. Bump their gums. 167.08, right? 167.08 omega. And that is pretty much the end of part A. Now, you got one more thing to do. And that is, if you come up here, you got to solve for part B. Part B is just using Ohm's Law, right? You're going to find V1, V2, V3, right? And to do that, you use Ohm's Law now. So, solve for V1, V2, and V3. To do that, he says V1, is using Ohm's Law, right? Is equal to what? Well, let's put it in perspective. I never changes. So I times R1. This is real easy. So that would be the same as saying V1 is equal to your current, which was this, 0.0444 amps, multiplied by, what was R1? Well, that was 250. It's just that simple. And then you'll get a V1 value. You can calculate that on your own. Next is V2. We'll do one more for you. I stays the same. You're using resistor 2. And we know what R3 is, so we just calculated it to finish it off. Okay? So this is going to be what? V2 is equal to, current stays the same, 0.0444 amps, multiplied by what? R2 was 188.78. Okay? And then you got to calculate for V2 and whatever you use your calculator. All right? So I brought you as far as you can. I want to slow down everything because we literally have 6 minutes of class left. So get all these notes, huh? Oh, you did it? I give you 10 points if you did it, Lika. 11.1? And that's volts. You got, that's 10 points here. You got V2. Alika's knocking it out for y'all. It's pretty cool. I hope y'all getting these notes down. Don't forget the exit slip information on the screen. You still got to type up. $8.38, yes ma'am. And 10 more for Alika. Okay, don't forget you need to finish up V3. Y'all know how to do V3, right? Should I write it out? So 8.38 for V2, 11.1, right, Alika, for V1? V3 is the same thing, right? You just use same I, and your R3 is here. We figured it out. So let's write that out there in case you forget. V3, these are the voltage drops or potentials. So that is going to be I is equal to multiply, V is equal to I times R3. This is V3. So that's V3 is equal to what? It's 0.0444 amps multiplied by what? Well, let's look at R3. We figured it out right here. And that's going to be 167.08 omega. All right, I'll leave it up to you to figure out what V3 is, but we got to finish up because we're about to get ready to go. We'll get you guys home. Okay? Don't forget you got a do to finish. You can do that on your own time. Exit slip, if I were you, get everything typed up in Google and try it out at home. You're just redoing what I did. This exit slip and everything, these PowerPoint, it won't change until tomorrow morning. So hurry up and get it done because once it's gone, it's gone.